Okay, so I'd like first to thank the organizers for this very nice meeting. I'm sure it's exciting times for them, young researchers, to be in such a new institution. I think it's a formidable opportunity for them also. So I'm going to talk to you about this work that has been done in collaboration with Giulio Birolli in Saclay and Laetitia Culiandolo in Jussieu. It's a rather technical subject based on Keldysh formalism, but don't worry, I know that Keldysh might not be your daily treat, so I will present to you kind of the, the few concepts that basically pave the road towards this result. But before I do so, let me present to you my main affiliation, my main institution, and instead of showing you the building, I will show you the view from the building. This is the rooftop view. So this is looking south. This is the hospital, military hospital, Val-de-Grâce. Then if you go a bit west, you have the Montparnasse Tower, the ugliest building in town. Then you have the Eiffel Tower, probably the most known building in town. And you have here somewhere, this is the Pantheon, where we bury our national heroes. This is the Notre Dame Cathedral. And this is the copy of the Montparnasse disaster. That's another university, Jussieu, Paris 6 University. And in the south, this is the Chinese Quarter. Okay. Please come and visit. Okay, so I'm going to spoil the story from the very beginning because the message I want to basically convey is that thermal equilibrium, be it quantum or classical or whatever you want, thermal equilibrium and the dynamics of systems which are in thermal equilibrium can be elevated to the rank of a symmetry. So that's the main message. So the symmetry of an action. So think of a system described by some field psi. That can be bosonic, fermionic, classical, whatever you want. In principle, you're able to write down some action functional, that is a function of this field, typically the integral of a Lagrangian, that describes not only the system, but the way that the system evolves in time, right? And I'm going to tell you how once you are in thermal equilibrium, you can actually show that the action, and it's going to be a Keldysh action that describes the systems, is symmetric under a field transformation. So I'm going to do some field transformation within my theory, and the action is going to be transformed and remain invariant. Okay, and why do we care about rewriting equilibrium dynamics as a symmetry? Well, first, it's very nice to have a very kind of symmetric principle for describing physics. This is what we like to do. And second is it has also some practical applications when you want to, because once you have a symmetry, you can derive all sorts of relations at the level of observables. These are the so-called Ward-Takahashi identities. So if I'm looking at, say, correlation functions, average over, so this is average over this typical action. Because this action is invariant, I can basically do a field transformation for the measure here, for the observables here, and I get this kind of identity. So this I can repeat for any kind of symmetry. Have translation symmetry, reversal symmetry. You can play this game and get some strong constraints on your observables for free. So let me try to first tell you that the idea that that equilibrium dynamics is a symmetry is an old it's not something very new. Classically, this is some common lore that equilibrium dynamics are a symmetry. You probably heard of detailed balance or Markovian system, which is usually expressed in terms of symmetry because it's a symmetry. So we worked on classical system, and we're able to generalize this idea that equilibrium is a symmetry for all classical systems: Markovian, non-Markovian, strongly coupled to the path, non-strongly coupled to the path, etc. So in all kind of contexts, in a first paper in 2010. And then the goal was set to go to quantum. So we need to generalize this idea that this symmetry idea to the case of quantum system, closed, open, And there's very recent activity actually in the high energy community working on hydrodynamics, quantum hydrodynamics, and trying to set up what are the effective field theories that conveniently describe these theories where you have slow modes, slow degrees of freedom, which are coupled to bath, equilibrium bath, but they are locally in equilibrium. They can be, say, at different temperatures, at different points. So they're driving the system out of equilibrium in some sort of slow way, right? So there is an intense activity these days on quantum hydrodynamics, and there people were also trying to find some symmetry principle to organize their effective field theory. Then more recently also in 15, there is a paper led by Andrea Gambassi, Tauber, and Dill that really got a very good shot at also going quantum and basically proposing what should be the symmetry for Keldysh described kind of quantum dynamical systems. And we later came this year with a strong proposal that not only allows to deal with symmetry, but also allows to break the symmetry, because as physicists, we like to have symmetries to organize our thinking, but we prefer actually to break those symmetries, and this is the history of the 20th century. So the second message I want to convey, if you have a symmetry in equilibrium, then when you go out of equilibrium, you break this symmetry. Okay, so now non-equilibrium processes can be seen as symmetry breaking processes. And if you look at how the action is going to vary under this field transformation I talked to you about, and I'm going to enter more details later, it's not invariant anymore, but it has some new term that is being generated by this transformation. It's a symmetry breaking term, and I'm going to make the point that this new term can be interpreted as entropy production. So quantum entropy production defined at the level of a single quantum trajectory. So in some sense, I'm going to go to, I will tell you more later. And the Ward Takahashi identities I had before that were based on the fact that my action was invariant or that my measure was invariant under the field transformation is now being broken. And I have some kind of relations like this where you see that the delta S that is in the measure here, which I'm going to say it's entropy, is going to basically, will appear on the right-hand side, and I will try to explain that this can be seen as generalizations of the fluctuation theorems. I'm going to tell you more in a minute. Okay. So before we so let me do the roadmap. So we have a few stops today. First, I'm going to tell you about what I think. To tell you about equilibrium dynamics, classical quantum, just to set up our discussion. Then what I mean by how do I go out of equilibrium, how I drive the system. I will recap some classical results on entropy production, textbook stuff. Discuss the recently discovered, like 10, 20 years ago, fluctuation theorems. And then okay, I will introduce to you the action, the Keldysh action I'm talking about, the symmetry once you're in equilibrium, and how this symmetry is being broken once you're out of equilibrium. So that's the roadmap for today. So let's start with Boltzmann, a bit younger than in your photo before, Stefan. So how are we in equilibrium? So we are in equilibrium if we prepare a system in equilibrium, say with a Hamiltonian H, temperature beta minus 1, and we evolve with the same time independent Hamiltonian. Then we're sure to be in equilibrium. So classically, I'm saying that if you start from a Gibbs-Boltzmann distribution and I evolve under Newton's law with the same time independent potential forces, then I'm assured to be in equilibrium. And quantum mechanically, the idea is that now the density, the probability distribution has now been to be replaced with a density matrix, Gibbs-Boltzmann, and you have some kind of unitary evolution. Of course, if I'm coupled to a bath that is also at the same constant temperature, I will stay in equilibrium. So as we learned with Stefan's lectures over the last 3 days, getting to equilibrium is another question. Getting to equilibrium might actually be complicated. In isolated system, we saw that some systems are actually expected to thermalize. Some are not expected to thermalize. The one with the one basically with many extensive number of conserved quantities, such as non-interacting systems or many Pauli localized systems. But I wanted also to make the point that in principle, as soon as you're coupled to some environment, some thermostat, then things are easier because you're basically coupled to a system which you impose to stay in equilibrium. So it will basically transfer its equilibriumness to the system you're being coupled to, right? So as soon as you have a thermostat, in principle, say this is for classical evolution, you have a thermostat which is in the form of this Langevin equation, these two heuristic terms that describe, friction and thermal agitation. In principle, will guide your system towards thermal equilibrium. Of course, it's not always the case. So even if you're open system coupled to some thermostat, some system might not thermalize, like glassy system, frustrated systems. So even there, I mean, it's not, even there, you don't need to be, you don't need isolated system to encounter troubles. Already with open classical systems, some of them will not thermalize. But for today, I really want to stay in the context of systems that are thermal. So that will be typically my initial state, and then I will time evolve them and look what happens. So please interrupt me at any point if you have questions. So let's make a first stop, classical first stop. So let's review a bit of stupid thermodynamics. Thermodynamics is the science of work, heat, entropy production, etc., etc. It was developed in the late 19th century, and 1 century after, people realized that they also needed to devise some other theory for small systems that are not not in the thermodynamic limit, for which you don't have really this equivalence of ensembles, and you need there was a need for coming up with some theory of thermodynamics for a single trajectory, so not averaged over anything, but for a single trajectory. For small systems, you need to look at single trajectories. This is typically what? I mean, this is typically the trajectory of a classical system coupled to some stochastic bath, right? And depending on the history of the bath, you will have different histories of your system, okay? And for each of these trajectory, you can actually define work as a functional of the trajectory. You can define heat, and you can also define entropy. This is stochastic thermodynamics. And the same way that for usual thermodynamics, you have a first law, which tells you that the variation of energy is work plus heat. And you have a second law that tells you that the variation of entropy is heat plus something, and this something is some creation of irreversibility, some entropy production, which of course, if you go very slowly in some reversible process will be 0, but if you pump fast in your system, then will be average, it will be positive in average, but for a single trajectory, you might actually find some trajectories for which the entropy is actually decreasing. So that was one of the result that came out of these studies. And actually, you can put this, the statistics on this guy, on this entropy creation, and you can actually formalize it in the so-called fluctuation theorem that were first derived by Galavotti and Cohen in the 90s. That tells you basically that the probability of entropy production for an experiment where I push my piston is related to the probability of destroying the same amount of entropy in a reversed experiment where I now pull my piston, typically, okay? And there is these exponential factors that tell me that, I mean, in the end, in average, it's typically I'm creating some entropy, but there are some paths for which entropy will be destroyed. So that's at the classical level. This was derived, and then people try to take all these ideas and push them to the quantum realm. Okay. Let's stay a bit classical for a minute. So it's not always easy to work with entropy, especially if you're an experimentalist and you want actually to measure something. So people were able to also express kind of similar laws, statistical laws on the creation of work. Not the creation, but on the statistics of work. So work is also a stochastic kind of nature to it. And they were able to derive, this is Crookes in 99, we're able to derive this kind of very similar relation that the probability of work during a forward process of pushing my piston is related to minus work, probability of minus the work in a reversed experiment. And you have still this exponential factor that tells you that, this is inverse temperature, this is work, and here you have just the free energy difference. So you're starting in equilibrium. In principle, you don't stop in equilibrium, But then you imagine that you can make your system relax towards equilibrium, and then you have a well-defined free energy function. And this delta F is the measure of, is the difference of the final free energy and initial free energy. So this was tested experimentally. This was one of, probably one of the first very nice tests that was, so there's Jarzynski. Jarzynski is also very, big driving force in all this, in this topic. And what they did here was they basically glued some DNA strand to some bead, metallic bead, that they were able to manipulate with a metallic laser beam. And you have to think that, here maybe there is water or there is some kind of thermal environment. And you can actually exert some force, constant force on this DNA strand and repeat the experiment and measure the work that you do for each experiment. So it's going to be different for each experiment. And then you look at the statistics of your results for work, and you can check that this works perfectly. So as I was saying, people quickly try to generalize these ideas to the quantum realm. Work fluctuation theorems were generalized, quickly after in 2000 by Jorge Cochan. Last week we heard about a talk by Kate Merch that told us that in some circuit-QED kind of architecture, they were also able to basically test this kind of relation in the quantum regime. Of course, in the community, there is still a lot of debate on even the the very definition of work. So you can talk with Prasanna if you'd like. He has very interesting to say about this. So work, heat is not super well defined. People are still debating how to define them correctly in the quantum regime. And for entropy production, it's even worse. So really, people don't really know how to define properly entropy production. Depending on the background of the people, they will propose different definitions. And a fluctuation theorem for entropy production has not yet been really pushed forward, I think. So in the rest of this talk, my goal will be to basically kind of address this question and give you my take on how we can actually define entropy production without making too much assumptions, but basically just using some symmetry and symmetry breaking arguments. Okay. Yes, questions? Right. Well, fluctuation in the sense that this is not a deterministic quantity. It fluctuates, and you can look at the statistics of the subject. And this is constrained by these kind of laws that people call fluctuation theorems. I must say that people went really further. I mean, this is really the beginning of the field. Then people started to develop extreme statistics, large deviation theory. So there is a whole very serious domain of research and intense activity to really go to every corner and test all this and make some prediction. It works. Okay. Okay. So let's dig in. So let me make a stop on formalism. So I told you that I'm going to use the Schwinger-Keldysh formalism for to get to my result. So let me try to place this formalism within the other formalism. So start with an equation of motion, maybe Schrodinger equation, maybe Dirac equation of motion. Choose your favorite equation, quantum equation of motion. If you're a condensed matter theorist working in equilibrium at temperature T, you might want to elevate this equation of motion to the path integral to field theory, and you're going to work with Matsubara kind of field theories, for which it's you have the whole sets of tools of field theories that you can use, diagrams and all approximations, finding symmetries in Lagrangians or et cetera, Monte Carlo. You have all this nice toolbox. If you work maybe at the LHC, maybe you want to do some scattering experiment, then you'd better probably work with a zero temperature quantum field theory. If you are working in soft matter with classical systems, typically your systems obey Newton's law or maybe Langevin kind of equations, and there you have a field theory, also path integral formalism that might be used is the so-called Martin-Sijarot's path integral formalism that people use. And if you want to do non-equilibrium dynamics of quantum many-body system, open, closed, then you have to find some mothership for all this formalism, and that's the Schwinger-Keldysh formalism. So the Schwinger-Keldysh formalism is kind of the centerpiece, and then if you work in different corners, you can simplify a bit this formalism. H bar goes to zero limit, you recover the Martin-CGROs. Equilibrium limit, you should recover all the results of Matsubara kind of theories, etc. So for the rest of this talk, I'm going to really simplify the kind of system I'm considering. I'm going to consider a system of non-relativistic real scalar field psi. I don't even care about space dependence. So it's really a zero-dimensional field theory, just time dependent, which is going to be described by a Hamiltonian, time-dependent Hamiltonian. So I'm going to prepare my system at some certain temperature at the initial time, and then I will evolve my system with a time-dependent Hamiltonian. And typically what I have in mind is really a stupid Hamiltonian where the time dependence will be in the potential, right? So here, to simplify the discussion also, I only look at closed systems. So it's prepared in equilibrium, I don't have any environment, and then at time evolve, and the only thing I can do to put my system out of equilibrium is basically through this time dependence here, which I'm okay to, I'm some external guy that can pump on my system. But of course, the results that I'm going to show you, they extend to much more generic systems, bosons, fermions, space-dependent, relativistic, if you wish. Yeah, so typically would be something like, would be, yeah, electric field would be perfect in the gauge. Well, no, the electric field you can, if you're coupled to the EM field, you don't have to think about, just you're coupled to electromagnetism, then you have, oh, no, you decided to put the electric field. I just put some time dependence, just a piston, some lambda of t. If you want to go into the models, of course, if you're trying to tell me that closed systems are not really closed, I agree with you. You're always coupled to the moon at some point, but completely agree. But again, this can be extended to open system coupled to some equilibrium band. Okay, so that's the slide. That's the that's the busiest slide of the talk. If you don't follow, that's fine. That's just 5 minutes about Keldysh formalism. It's not really absolutely crucial for the rest of the talk. And we had already some introduction yesterday by Rajdeep about the Keldysh formalism. So just to tell you that when you want to compute some time-dependent observable, some time-dependent quantum theory, what you typically do is that you trace. This is the Heisenberg representation of my operators. You trace this kind of object with respect to the initial density matrix, which is here equilibrium. So here I'm considering time-independent Hamiltonian. I'm really considering the most simple setup. So time-independent Hamiltonian. So you see that you have this kind of forward and backward kind of evolution that, as we saw yesterday, you can basically collect into this kind of time contour. And so this is in the operator formalism. Here I reduced my expression by introducing this time-ordered contour that basically, so this piece, this vertical piece here is to deal with this initial density matrix. Basically, it's a Matsubara kind of time, measuring time integral. And then I'm going forward, I'm measuring my stuff, and then going backward. So if you want to go from operator formalism to a path integral, what you typically do is to introduce at every time step some resolution of the identity. Okay, so you Suzuki-Trotter decompose your time evolution, your unitary operator. You introduce this decomposition of the identity, which is for a real field would be something like this. Right? So you introduce this at every time step, and then you basically convert the Hamiltonian picture here into a Lagrangian picture. So I'm not going through the derivation. This is pretty much standard textbook. So each time, so now instead of doing it for just in zero temperature field theory, you would do it from minus infinity to plus infinity. Here you do it along this, so-called Behm-Kadanoff contour, but the math are exactly the same. And then you end up with this kind of path integral formalism where you're summing over all possible trajectories of your quantum field that live here on this equilibrium branch, plus branch, minus branch. This is your action, which is basically the integral of the Lagrangian of your system. And here you're measuring something, so some operator at time t here on the plus branch. Okay, so the next step for me was going to to take a bit of a step back here, and I'm going to argue that actually this contour, this Behm-Kadanoff contour, can be deformed to generic contour in the complex plane. So instead of working with times that run on the real line here, I'm going to be able to reparameterize my physical time by some complex time. Okay, so I'm going to go from this kind of theories here defined on this kind of contours to to the same theories defined on some other contours. Okay, so I'm not changing the physics. I'm just changing the formalism. It's kind of a gauge symmetry here that I'm going to do on the formalism. And the way that I can play these kind of tricks is by working instead of inserting these kind of identities at each point in time when I was in my operator formalism. Now I'm going to introduce some kind of generalized resolution of the identity that will know about the Hamiltonian, and that will also be parameterized by a new function theta of t. Theta of t is a complex function defined on the Keldysh contour, and that can really choose at will. Basically, it's going to be a free parameter. So I have a new parameter which is a complex function of time defined on the complex plane, and I claim, you can do the math, that instead of working with the time t here, now you can work on those contours that are being parameterized by a new complex time, tau, which is the original time plus this function theta of t, which is my choice, total choice. So instead of working with fields defined on real time, now I'm working with fields defined on these complex times, yes. No, I'm not assuming anything on the analytic structure of my theory here. I am just playing with this kind of identity, which is free. I'm inserting it, and I can see that I do the math, and I have to recompute now what is the new Lagrangian that comes out. So in principle, when I was doing this trick, inserting the identity here, I was transforming my Hamiltonian into a Lagrangian, the usual Lagrangian that we all know. Here I'm going to insert this one. I'm going to get a new Lagrangian, and we're going to discuss this a little bit. So it's going to be a deformed kind of Lagrangian, and this Lagrangian lives happily on this kind of contours. But I really make no assumption whatsoever on the analytic structure of my underlying theory for now. So the only I see. This is very related question. I think. So the only requirement I have is that it's invertible, so I can go from tau to t easily. It's not multi-valued or stuff like this, but the slope can be positive or negative, because typically in Schwinger-Keldysh kind of approach, indeed, okay, let's discuss this later. I think I see what you mean, but this is not this. Yes. Yeah. Okay. Good. Theta should be relatively smooth. Yeah. Theta should be. You should be able to. Yeah. I think his question was whether or not theta can be an increasing function. So basically, he was asking, is this right? Anyway, in the next slides, I'm going to work with very simple thetas, constant actually. So okay. So in some sense, I generalized a bit the Keldysh formalism to have a new degree of freedom. So I'm more free to do whatever I want. I'm really not, again, my point is that I'm not changing the physics. I'm just rewriting, and since I'm not changing the physics, principle should not, the underlying physics should not really matter. So I'm really getting a bit, some new clothes, but I'm not changing anything. So let's start with equilibrium, and then we're going to go out of equilibrium. So in equilibrium, I propose, and that's my choice, to work with the following contour. So it's a contour that is kind of very symmetric. So you have in blue here the plus field that starts here at I beta over 2. There is an H bar here. And then that's constant for the whole evolution. Then it goes down and goes backward in time like this, okay? And I claim that if you do, if you do the computation, the theory that is defined on this contour for a constant Hamiltonian prepared in equilibrium, so really stupid, static quantum mechanics. The Keldysh action that described what's going to happen to my system is basically the integral over this new contour of the usual Lagrangian. Okay. Okay. And the claim, the symmetry claim, is that if you look at this action and you plug in the following field transformation, I call tau beta, T beta, so it's a transformation of the fields. Psi plus, psi minus are going to be transformed into themselves, actually. So psi plus of tau that lives on this contour, I send it to psi plus of minus tau plus I beta over 2, and the psi minus of tau, I send it to psi minus of minus tau minus I beta over 2. So I claim that if you play this game here in here, what you're going to get is that this symmetry is going to remain invariant. Oh, sorry, this not symmetry. This action is going to remain invariant. So that's the symmetry. That's the thermal symmetry, which is stated here. So remember that, I didn't tell you about, I had some prefactors here. These here, there's the partition function at initial time. I now upgrade them to free energy. So I basically put them in the exponent so that they now I like to put them here. They stay close to the action, but so they don't transform. The action is transforming, is being transformed into itself. That's the symmetry. So if you look at this field transformation, it's quite a simple transformation. Actually, it's kind of universal to any kind of system. So here, psi is a boson, it's a real field, but it could be boson, Fermi. You get the same kind of so it doesn't know about the details of the system. The only thing it knows about is the temperature. So that's the only information. And basically what it does is some kind of time reversal plus some kind of imaginary shift that is very reminiscent of all these KMS conditions and people deriving work fluctuation theorems. We're also, as we discussed yesterday, we're also using this kind of tricks to get there. So it's a discrete symmetry. So it's not a continuous symmetry. It's a discrete symmetry because it sends t to minus t basically. It's involutive, so if you repeat it twice, you go back to your initial point. It has a unit Jacobian, etc., etc. So once we have this symmetry of the action, we can derive very nice things for free. So we have these so-called Ward-Takahashi identities. So if you look at correlation function of your field at different points in time or space, if you had kept space, they can be shown clearly, easily to be equal to their transformed version under this symmetry. And since the action over which you're doing the average is invariant, then you get for free this kind of relations. And if you apply it to Green's function, what you get, so Green's function defined on this Keldysh contours, you have the plus and minus fields. So in principle, you have 4 types of Keldysh functions. Using this symmetry, what you can show is you can show the so-called fluctuation dissipation theorem that was already talked about a lot in this conference, in this workshop in the last few weeks actually. And that basically can be stated like this, which basically, here is the classical limit of this theorem. It basically says that the way that the system is going to respond to some linear perturbation can actually be predicted by not doing the perturbation, but looking at the correlation function of your system in equilibrium. It's a very strong theorem. Okay, and so we did the symmetry part, but now we want to break the symmetry. That's the fun part. We want to break the symmetry. We want to go out of equilibrium and look at what happens to what are the symmetry terms that are the terms that are being generated and that breaking the symmetry. So let me now consider this time-dependent drive, your drive, your choice. Yeah, you can work with complex fields, Grassmann fields. So the Jacobian will always be, you mean the Jacobian of the transformation? The Jacobian here will always be unity. At least in all the cases I checked. I mean, it's so simple. I mean, it's just, you're basically taking the information that was, I mean, something I could have said is, I mean, you can almost graphically see that the symmetry is working. Take this blue piece here and rotate it 180 degrees around that point, and you see that it's invariant. Do the same for the red piece here and rotate it around this point here by 180 degrees, and it's invariant. So already I just showed you that, you know, this piece of the action is invariant under the, and then you have to check that this piece also is invariant, and then you complete the proof. And then the Jacobian is unity, so you don't have to take that. Yep. Yes, yes. Oh yeah, yeah. Theta is beta by 4 on the plus side and minus beta by 4 on the minus side. Yes. Throughout the talk, yeah, now I decided this contour is nice for equilibrium purposes. Now I'm going to go out of equilibrium, but still I'm going to stick with the same contour. I could probably go to some different contour, but that's the most convenient contour to express things and to get immediately the physics out of it. Yeah, if I had not deformed, I would. Yeah, if I had not deformed, I would not have been able to. At least I would not have been able to find the symmetry. Yeah. So the roadmap is typically you start with the usual Kadanoff-Baum kind of theories, you deform them towards this contour, you do the symmetry thing, and then you recollapse to the original Kadanoff. You redeform in the way you redeform back. You do this kind of TST transformations. And then you get relations for usual Kadanoff-Baum kind of theories. Okay. Yeah, so if you put your favorite time-dependent drive in action, then the theory, the action that I showed you that was living on this contour has now to be a bit modified. Before it was just the time integral of the original Lagrangian of your system. Now it has another piece. So now the action that describes your theory on this new contour, and this contour C beta, has a new piece, which is which only appears if things are time dependent. And I'm not going to enter the the proper definition of this object. That's actually quite ugly expression, but it's new, it's there, and it's only there if you're going out of equilibrium. And now, if you play the same game of looking at the action, so this is always this free energy piece that I basically pull out from my original initial partition function, which I like to put upstairs, very close to the action. If I look at how the action is now being transformed under the symmetry transformation that I had before, so it comes in two pieces. So there's these first terms here, which are very reminiscent of what I had before, except that, basically these are terms that kind of supersede the former terms that I had, that they are basically free energy and action functional that correspond to the reversed experiment. So if I was pulling in my piston in the forward experiment, now I'm pulling out the piston, that would be the free energy and the action that correspond to that experiment. But this piece here is giving rise to a very new term, which comes in two pieces. There's first this variation of free energy, and I think this is easy to understand what's going on here. But there is a new object here, which I called sigma, which is functional of the field trajectory, which I wrote the expression here. So sigma is the time integral over this Keldysh contour of the expectation value of this blue operator here. So it's not particularly nice looking, but I can take different limits to try to understand what is this object. I can take the classical limit, h bar goes to 0 limit, and I see that this object is basically work times inverse temperature, and that this is basically the power that is being generated by the force I'm exerting on my system. I can take some averages. I can take some different kind of limits. I can take some reversible process limit where I'm slowly varying this time dependence here in the Hamiltonian to see what I get back, etc., etc. And I think this is the topic of the next slide. And in the end, I can conclude that this new object that came here in yellow is actually a measure of irreversibility for a single trajectory, a single quantum trajectory. Okay? So I will claim that this guy here, this double guy here, is a measure of the irreversibility which is being created quantum mechanically in out of equilibrium systems. So again, it comes in two pieces, this just free energy difference here, and this new sigma functional, which I give again the expression here. You can check that, you can check analytically that the average value of this quantity is positive, as you would expect for a creation of some creation of entropy production, as we already discussed in the classical case. Okay, the classical limit works perfectly; it gives you back what you expect classically. And you can also work with very slow processes, reversible processes, and see that this guy, the average of these guys converges towards the usual quantum definition of work. But it's more than work. So basically, work is the H. You have this guy is work plus some H bar corrections plus some quantum corrections. So it's kind of a new object. Yes. Yes. No, I'm not thermalizing. So you're talking about this guy here. So this is. I'm not actually thermalizing. This is like some thought experiment where if I had then couple my system at the end of the experiment, couple back my system to the bath and let it relax. That would be the operational definition of this free energy with the same equilibrium bath that I used in the first place too. Yeah, some kind of formal and yeah, in the very phase. Yeah. I don't know. Not evident to me, but maybe in some formal way of thinking. Yeah, this is some analogy. And okay, and once you're here, the fluctuation dissipation comes for free. That's not a very. I mean, once you're here, fluctuation dissipation will come for free. It's not particularly, but still, I mean, it's nice to have an expression now for the quantum fluctuation theorem in terms of this new quantity, which I think we can now call irreversibility production, if not quantum entropy production. I don't know. Yeah, so that's and then there is still, I mean, I think open questions is to kind of understand what is this operator. Is it really some entropy production operator, and what are the properties of this guy? It's very Hermitian operator that principle could be measured in small system, in CQE, small qubit system, could probably measured. Okay, so that's still to be discussed. And I want to finish by just recapping what I told you. So the main message was that equilibrium dynamics are a symmetry, non-equilibrium dynamics are a symmetry breaking process. The terms that are being generated that are symmetry breaking, the symmetry breaking term are actually can be identified as entropy reduction. We knew this in the classical case from a long time ago. Now it's been generalized to the quantum case, I think. And what we get is so-called fluctuation theorems based on entropy production in the quantum realm.
Camille, so I was just wondering if there is any way of thinking about steady state in, so once you have this time dependent thing, within your description, can you kind of say anything about that?
Yes, so you mean non-equilibrium steady state?
When you have like, steady state, whether there's something you see in terms of your...
Right, so for a non-equilibrium steady state, you need a drive and a bath, maybe. I mean, I don't know if you can get a non-equilibrium steady state without a bath. Usually you inject energy on one side and you with work, and then you need to pull it out.
You cannot think of steady state in this language at all, is what you're saying? Or just to make sure I understand.
Okay, I'm saying, okay. Say for systems that do not thermalize, they will get some steady state that is not thermal. And so the thing is that this quantity, this operator here, as soon as your Hamiltonian stop being time dependent, so say you do something in the beginning and then let evolve, as soon as this guy is not time dependent anymore, this is going to be 0. So this is more of a people in the classical realm, they would call it dissipated work. It stops being something as soon as you stop acting on your system.
Okay, so have you thought about something like a quench protocol? Say you switch on h of t for some time, and then it becomes time invariant again, so your derivative would vanish.
Yes.
So is there something like emergent equilibrium?
Yeah, very good. I mean, this is something that that's a very good question. There are actually, yeah, and it's but I don't know. And there is also kind of the reverse question, which is, can you set up your stuff such that you have, in principle, your theory is is symmetric, but you spontaneously broke this symmetry. So you have some kind of aging that you basically maybe the bulk of your theory is symmetric, but maybe some boundary term will actually break the symmetry, and you will fall out of equilibrium by some kind of some kind of aging. These are these are good